you have to deal with fractions, and that can be kind of scary at times. So we're going to talk about, some strategies that I would use here. You have a lot of options. Um, I like to, Most of the time, I like to try to get rid of any parentheses if I can. So the first thing I would do in a problem like this is I would distribute to get rid of my parentheses. Now, when you do so, you're just multiplying fractions, which, guys, multiplying fractions is probably the easiest thing you can do with fractions. It's just multiplying the numerators together, multiplying the denominators together. So we would have negative 20 over 6. Now, yes, I could reduce that. I'm not that worried about it because I know that this is going to be a long process, so there's going to be an opportunity to reduce this at some point. Also, I find that when I'm solving equations like this, because there's so much going on and so many different steps that I have to make, sometimes I forget that I have to keep the variable. A lot of times I'll just not write the variable and then end up making a mistake because of that. So just take your time, okay? So then we'd have minus 8 over 15 equals, so we'd have 13 over 4r. And then, so 13 times 5, that's 65 over 12 minus 27 over 8. So it doesn't look a whole lot better, but here's the thing. We would like to be able to get common denominators here. Okay, so you have two choices, really. The first is you can just get everything with a common denominator and then go from there. Or you could multiply everything by the common denominator right now. Depending on your comfort level with fractions, it's gonna kind of drive which direction you go. For now, let's go ahead and get a common denominator in all of our fractions. Now, the common denominator is not a large number, so it's not a small number, but you have to kind of think about what's if you can, the smallest number that we can get all of our denominators to be. So if you guys have any ideas, go ahead and type it in the chat if you think you know what you could do as a denominator. And if you did this one, you might already know. Oh, someone's got to have an idea. Don't be afraid. We're all in this together. I'm seeing some responses here. Good. We've got 60 and 120, kind of half and half right now. Both of those have the same number of people saying it. So let's talk about 60. So in order for a common denominator to work, you have to be able to multiply each of our denominators by an integer and get that common denominator. So if I look through this, definitely 6 times 10 will give me 60, 15 times 4 will give me 60, 4 times 15 will give me 60, 12 times 5 will give me 60, but we run into a problem with 8, right? Because the closest I can get is 8 times 8, and that's 64. So it was good up until that last fraction, and that's the one that's going to cause us the problems here. So let's try 120, and I think that'll work because 6 times 20 will give you 120. 8 times 15 will give us 120. 30 times 4 will give us 120. 10 times 12. And then we said 15 times 8. So all I'm doing here is just showing that we can get a common denominator, right? And I'm actually working through that process. Now, I'm not going to completely finish this, but let me kind of talk you through what you do. So let's say that I had, that's what you're going to have to do. Now, like I said, I'm not going to go through that whole process because part of what I'm asking you to do is make sure that you can do this on your own. I'm giving you that push, and I want you to now try to continue where we left off. So you would have to multiply all of your fractions out and then multiply every term by the common denominator. And that's going to give you an opportunity to get rid of all of those denominators, and you'll have a nice linear equation that you can solve. So that's kind of what you would do then for for those two problems, 7 and 8. You would have to get a common denominator in each fraction and then multiply by that common denominator. Does that help with that section? Just give me a yes or no in the chat. And if no, I may ask you to kind of tell me why. But it looks like yes, yes, lots of yeses. Okay, fantastic. So the second section, I guess kind of tied for second, is 17 through 20 and 21 through 24. So let's take a look at those. 17 through 20, yeah, the ones with the exponents, and then 21 through 24. I'm not surprised by those at all. So let's think like this. I don't know. I'm just going to make this up real quick. 1/7 x equals 2/7. So let's say I have that, okay? If I were to get my common denominator, and this is much more simplistic than the one we just did, I would have to multiply this by 7. I would have to multiply this one by 5/5 and this one by 5/5. And what I get, so that's where we are in the previous problem, but what I get here is a fraction that's going to have all the same denominators. So it's going to be 21/35 minus 5/35x equals 10/35. And here's what we can do with this. We can multiply every term in this equation by our common denominator. And I think I asked my previous Algebra 2 class yesterday if they remember giant ones. And I think that was a topic that you did talk about in Algebra 1. So the idea of a giant 1 is going to come into play here. If I multiply by the common denominator, and you're going to learn with me, if I see one fraction, I make everything a fraction. So when I'm multiplying by that common denominator, I'm multiplying by that common denominator over 1 so that it's easy to multiply the fractions together, but also so that I can easily identify those giant ones. All right, so what that's going to do is it's going to eliminate all of my fractions and give me something that looks like this. So in the previous, head and talk about maybe 17 through 20 first. Actually, you know what? I'm going to talk about 21 through 24 first because I want to talk about 21. I think this will help us when we get a little bit. Maybe not. It's okay. We're going to talk about this one first anyway because I like to do things out of order and keep you on your toes. Okay, so 21. Guys, when I ask you to solve for a particular variable, what I'm asking you to do is find a way to get that variable, just that variable, all by itself. So you really need to think about how you solve an equation for a variable, right? When we're solving an equation, we're actually undoing what's happening to that particular variable, but we're undoing things in the opposite order of operations. I don't know if you've ever really thought about that, but when you're solving an equation, you undo subtraction and addition before you do multiplication and division, and that is backwards PEMDAS. So that's kind of what we have to think about here. We have to undo what's happening to that variable, but in the opposite order of our order of operations, which means any exponents are the last thing that we undo. The first thing in this case that we're going to undo is that multiplication, because really that's what's happening right here, between pi and r to the 2h power. There's a multiplication happening there. So the first thing I have to do is undo that by dividing both sides by pi. Now, we all know that pi is an irrational number. You know, we sometimes use 3.14 as an approximation for it. It's just a number though. Okay, so we're just dividing by a number. No big deal. So what we have here is just s over pi equals r to the 2h power. Okay, so what's interesting here is if I had just written this, r squared, if I just said s over pi equals r squared, probably I would say most of you could tell me how to solve that problem. To undo something that's being squared, we would take the square root. Julia, yes, I'm going to post this. I'm recording it, so I'll post it on Classroom. So to undo the squared, I take the square root. Well, if I had, instead of squared, what if I had written, r to the fourth power? Then we would do the fourth root of both sides. If I had written r to the, 379th power, then we would do the 379th root on both sides. So all we're doing here is we're just taking a root, okay? We're going to take the 2h root of both sides. Now, it's not pretty. It's not something that you're used to seeing, but that's what we're doing. So I would take my s over pi. I'm going to take the 2h root of that, the 2h, the 2h root of the other side. And what that will do is it's going to undo the 2h power. And that's just going to leave me with an equation that looks like this. The 2h root of s over pi equals r. Maybe you know how to use powers that are not integers to undo a 2h power. And that's fine. We will talk about that a little bit later this year. If you don't know what I'm talking about, that's okay. I do touch on, I think it was, 24 for just a second too. So 2 pi r squared plus 2 pi r h. And this time we want to solve for h. So the key here is understanding that this is not like what you did on the previous worksheet in that there's not multiple terms with h in them. There's only one term with an h in it. So once again, I'm thinking about undoing in the opposite order of operations. What that means is whatever's happening to h, I undo, but I undo it in the opposite order that I would normally use order of operations. So I look at this and I think about the fact that, as ugly as this is right here, that is just a number. Okay, we just don't know what number it is because we don't know what r is, but that's just a number. So we're saying some number plus 2 pi rh. So to undo things, the first thing I'm going to have to do is subtract 2 pi rh from both sides. So that's going to give me an expression that looks like this. Equals 2 pi. And I think I was saying 2 pi rh. It should have been 2 pi r squared. I apologize. So we subtract that 2 pi r squared from both sides, and now we've got it a little bit better. Remember, our goal is to try to get this by itself. We want to get h by itself. So then I ask myself, what's being done to h right now? Well, right now we are multiplying h by 2 pi r. Once again, whatever that product is, it's just a number. It's just an unknown number right now because we don't know what r is. So to undo that multiplication, I'm going to divide. So I'm going to divide, I keep forgetting to go back to the pen after the highlighter. I'm going to divide by 2 pi r. Now, there's a couple ways that you can write your answer here. So first of all, when I divide by 2 pi r, I end up just getting h, which is beautiful. That's what I want. If you write your answer just like I have it there, a minus 2 pi r squared all over 2 pi r, that's great. I'm okay with that. In fact, I prefer that right now because the other option is to split it up into two fractions. And sometimes that can get confusing, and I don't want you to do any more than is necessary to give me a complete answer. What I don't want you to do is think that you can start using giant ones here, because there's not actually a giant one. One of the biggest rules with a giant one is the only time they can be used is when you have a product. So if we look at our numerator, this is not a product. This numerator is actually a difference because it's being subtracted. So we can't actually get rid of any giant ones here, so to speak. So our answer is literally just what I have written there. without worrying about simplifying it, this is fine. The only simplification that could take place would be to split this up into two fractions. And whether you do that or not, I don't care, because both are, to me, an appropriate answer. Okay. Would you, Max, I think he's calling me Walmart Khan Academy. I'm not sure if that's a compliment or an insult. All right, so let's, did that help with that section? So give me a yes or a no there. I see some of you nodding your heads, but if you want to type in, because I can't see all of you, I can only see 9 of you on the screen right now. Okay, fantastic. So the other section, 17 through 20. So what's interesting about 17 through 20 is that we'll actually spend some time this year looking at how to solve these with something called a logarithm. And I'm not sure if you've talked about logarithms yet. I don't think you have, but it'll be one of our topics for the year. So yeah, so let's talk about 17, and then we'll kind of touch on some of the other ones as well. The reason I chose 17 is because this is actually set up for you to solve pretty quickly. The idea here is you've got the same base, 4, raised to two different powers, but what you know that has to be true here is that the two things have to be the same. So I know that whatever 4 on the left-hand side of the equation is raised to, it has to be the same as 4 on this side. So what that kind of really tells me is that these powers must be the same. If they're not the same, then this is not an equation. So that allows me to set up a really fast equation where I can just say, okay, well then negative 2n plus 2 has to be the same as 3n. That's the only way those two equations, or that equation, is going to be equal. And that's a really simple equation I can solve. It's a linear equation, should take you about 30 seconds to solve. But that's kind of, it was sort of set up for you to solve easily. And maybe you guys were able to figure that one out without too many issues. One that's maybe not, go ahead and look at easy to solve. So something like maybe 19, where we have 216 to the negative 3x equals 36. Okay. The hard part about this one is the bases aren't the same on both sides. So in order to actually solve this, we have to sort of take an intermediary step first. We have to force it so that the bases are the same on both sides. Now, like I said, later in the year, we're going to talk about logarithms, and you'll be able to solve this without necessarily doing this. It'll be much quicker to solve it with a logarithm. But until we get there, this is an appropriate solution. So I have to really be comfortable with the powers of numbers up to like maybe 9 or 10. Even 12 might be appropriate. But I need to know, what are all my powers of 2? What are all my powers of 3, 4, and so on. If I think about, and not all, obviously there's an infinite number, but maybe the first 3 or 4 powers. If I think about what number, my question is, what number could I raise to a power that's going to give me 36, but then a different power of that same base would give me 216? So you could start kind of playing around with this a little bit and maybe do some guessing and checking. 2 would work, but it gets to be pretty high powers and it might take you a while to figure that out. 6 actually works here because, and you might think of that right away because you know that 6 squared is 36. Okay. And we know that 6 cubed, well, hopefully you know that 6 cubed is 216. If you don't know that, now you do. So 6 squared is 36, and 6 cubed is 216. So what I'm going to do is I'm going to just replace 216 with 6 cubed and 36 with 6 squared. So instead of 36, I have 6 squared. Instead of 216, I have 6 cubed. Now here's the thing. Looking at your original equation, that 216, which I'm now writing as 6 cubed, is raised to the negative 3x power. And that's important to not forget that because it'll throw everything off. So now we're sort of in that same situation we were in a minute ago. where the bases are the same on both sides. So we really have to think about what's going to make the powers equal. And the only thing that might get in your way here is understanding your power rules. When you have a power being raised to another power, do you remember what you do with those? Which mathematical operation do you use? Does anybody remember that? And you can just type it in the chat if you remember. When you have a power raised to a power, what do you do with those two numbers? Yes. Yeah, good. Multiply. Okay, so I'm going to multiply those two powers together. So this is really 6 to the negative 9x power equals 6 squared. And now we're right back to that problem in the, I think it was number 17. So you can take the two powers that you have written here, negative 9x and 2, and set them equal to each other and solve. Okay. Does that help? Again, give me a yes or no in the chat just so I know if we have to talk about anything else. Awesome. Let me touch on 25 and 26 because, yeah, those are a little scary. I'm not going to necessarily solve anything here, but I just want to make sure that you understand at least what's being asked, and especially on number 26. So with number 26, what I'm asking you to do, I want is, you know that y is equal to x plus 3 over 1 plus 2x. Okay, that's a given piece of information. We know that that statement is true. What I want you to do is find a way to represent the next expression with only in terms of x. Now, what that means is I'm going to take this y plus 2 over 1 minus 2y. I have an expression for y right here. Okay, that's what y is. I need to put that entire expression into that second expression everywhere I see y. Now, the hard part there is not in the substitution. That's probably going to be pretty easy. The hard part is trying to simplify it. And I'm challenging you here. I'm telling you right now, this is a challenging problem. And I just want to see if any of you can actually see it the whole way through. But that's my little push on that problem. Substitute in that expression, x plus 3 over 1 plus 2x, for y in that second expression, and try to simplify it as much as possible. Okay, so that's what I want you to try to do there. 25, you are being asked to solve that expression for x. So I would probably start by distributing as much as I can. And the big question I had yesterday with that problem was right in the beginning. So you have, let me just write the left side of the equation here. Okay, you have this. A lot of people got confused about what to do here. Well, here's the thing. We know that multiplication is able to be done in any order. And what that means is if I had like negative 2 times 5 times 3, I can write it as negative 2 times 5 times 3, or I can write it as negative 2 times 3 times 5, or 5 times negative 2 times 3. I can rearrange those terms, and that product will be the same no matter how I rearrange them. That's kind of what I want you to think about here. We're multiplying negative 2 times y plus 4 times 3. I can rearrange that so that it looks like this. And then and then do my multiplication from there. So maybe I would write this as negative 3x minus 6 times y plus 4 minus 7, and then distribute the 6 and go from there. Remember, your goal is to solve for x. This is similar to the problems on that previous worksheet, and I have a solution to that uploaded to our classroom as well. But you're going to have to gather up all those terms that have x in them and then factor that x out. I had a few questions on some of the other sections, and I'm going to hold off on those for just a moment, and I'll tell you why. We've gone through and we've talked about these. What I want to do is have you guys go back and either on this worksheet or the previous worksheet, I want you to try to go back and make corrections or finish, depending on where you are. If you haven't finished yet, you're going to have time to finish. If you need to make corrections because you know you messed up somewhere, make your corrections. I'm going to leave, and I want you to stay in the Google Meet, but I'm going to leave this open because I want you to be able to come in and out and ask questions if you have them. And if you have a question on a particular problem, I can help you with that maybe more individually. So here's what I'm going to ask you to do. Go ahead and you can turn off your cameras and you can start working. Definitely take a break. You know, we've been going for about 40 minutes here.